Good afternoon. This slideshow is going to go into a little bit more depth than we've been able to do in class about external evidence for validation arguments. In some of the old-fashioned ways of looking at validity, this came two separate areas of approaches to validation. One was under criterion-related evidence or predictive evidence, and one was under construct validity. But because they both relate interpretations of scores from scales to other scales, they are both considered sources of external evidence. So there's pretty much all based on some form of correlational analysis. And the two types of investigation that I'm going to discuss right here are criterion relationships, where the criterion is considered a gold standard or an ultimate test-based, or not necessarily test-based, ultimate source of decision-making that is measured without error. And one uses a test to predict that, sometimes because that only appears later. And what you want to know is someone on a trajectory now to achieve or not achieve a certain outcome later? So for instance, it wasn't a validation study, but a study that I looked at, or actually that I was involved in, used both the variables of high school readiness metric for college and CUNY placement exams. So the CUNY placement exam was measured with error, but was a criterion measurement in that it was in the future. It was a predictive study. The other approach to this is not to make a prediction. So the measures can be taken concurrently, and it looks for both convergent and discriminant evidence as an argument for validity. So you're looking to see whether an instrument's scores yield interpretations that are consistent with scores from similar measures and inconsistent with scores from measures of different but related variables. So plausible variables, but different constructs. So we're going to look at both of these. So the first question is, if we're looking at predictive validity, how do we do that? And as I said, this is correlational. This was a study that I was involved in where we were looking at the predictive ability of an early exam to relate to overall end of semester performance. And the purpose of this study was whether or not the first exam scores could be useful, interpreted in a useful way to screen out students who were unlikely to fail. So what we did is we took exam 1 scores from multiple institutions, not just CUNY. And those were early exams. This was all in undergraduate first semester chemistry. And we put those on standardized scales. So exams from multiple institutions could be used in the study. And then we correlated those with course performance with the effect of the first exam removed. So otherwise the correlation would be inflated because the predictor variable would be included in the predicted variable. So we said, if there had not been the exam 1, would a student have been likely to pass the course? And that was passing the course, I believe, had about a overall performance of 0 or maybe 1 standard deviation above average. But the real question was at how many standard deviations below average was the chance of passing the course very low. And we used that to make the argument that you could use the first exam as a screener at the low end of performance. Say, I think we ended up with like -2 standard deviations below the mean on the first exam, predicted failure on the course overall at a fairly respectable level of correctness. And we'll look at correct decision-making later. But it started out with a scatter plot and a correlation, and then the squared correlation, which you see there as r squared equals 0.53. In other words, 53% of variance in course performance could be accounted for by the first exam. So that's pretty good predictive validity, and it actually compared favorably with the use of placement tests for chemistry, which of course have to be paid for and kind of don't give students a chance. So once students had been put in this course, and hopefully not, but some of them would fail or place below, perform below 2 standard deviations below the mean, they could be counseled to a course at a slower pace. So what you're looking for in terms of the outcomes of a predictive test depends on your purpose. So going back to the previous example, we were not particularly interested in all those people who performed well on exam 1. We were not interested in screening them out. What we were interested in was preventing students from failing. So we were interested in the students who were failing the course and whether they could be predicted by failing the exam. So the people on the far left of the scatter plot. Similarly, we can use with a criterion, the failing course is a pretty good criterion because although a test can be, will have error, random error, the course grade is a criterion measurement in that it is the basis of a decision. It, whether or not it is established with error kind of doesn't matter. It is taken later as an error-free measurement. A more stronger example of that would be, for instance, a medical test. And I'm just going to use here the example of a hearing test, such as is routinely administered in school settings and yields, first of all, a very simple test-based positive, there's a hearing problem, or negative, there's no hearing problem. Whatever score someone gets on that is divided by a cut as to, we covered cut scores, a clinical cut score as to whether or not that person is going to proceed to further diagnostic issues. And you see your diagnosis along the top of this box, which is going to be after more extensive testing, does that person meet clinical criteria for hearing impairment? So you have, let me get my annotator. You have, and I went through this in class, multiple decisions available here. The circled decisions are what are called the correct decisions. They may not be called that, but that's what they are. They're the correct decisions. In other words, These people in this quadrant, when they took the hearing test in their schools, it said, the results said, this person likely has a hearing problem. And when they were further diagnosed in a clinical setting, then that result also said that they had a hearing problem. In the other quadrant that is circled, you see that when they took the test in school, the outcome said they do not have a hearing problem. And if they had been diagnosed professionally in a more clinical setting using clinical criteria, that diagnosis would have turned out to be correct. Now, we don't, in the school setting, perform this, as it were, experiment. We don't go ahead and put people who test negative for the hearing test in for diagnostic testing, but during validation of a clinical measure, they do. They send people on for the diagnostic testing to find out how many people who test negative, or the proportion of people who test negative, do actually not demonstrate a hearing loss on further clinical diagnosis. So we have such and such many correct decisions. And those are what we call true positives and true negatives. You also can have incorrect decisions, and those are false negatives and false positives. A false negative is someone who fails who is shown not to have a hearing problem, but had they been in the clinical setting, they actually did. These people are problematic because in practice, we're not going to send them on to the clinical setting. And so this is problematic. These are people who we say, oh, you don't have a hearing problem when we look at them in school. And had we sent them to a clinic? Yes, they did. These are what we call false positives, in that we thought when we looked at them in the schools that they had hearing problems, but when we send them to the diagnosis, they don't. So there are various statistical ways that we look at the accuracy of a test when it is used to make binary decisions that yield or that are associated with further binary outcomes. And those have to do, first of all, with the overall rate of correct decisions. So 500, this isn't listed down here, but 560 over 1,000, so 56% of these decisions are correct. That isn't particularly high, but one of the big concerns that you have is, what is the purpose? Is your purpose overall correctness, or is your purpose perhaps, like in this picture, just to look at a certain type of people? So here we can look at these statistics called prevalence, sensitivity, and specificity. And I'm not going to go into all of these. And I have actually some of the numbers wrong because I changed the slide, and this should be 40. This should be 320. This should be. Okay, I corrected my math in here. Excuse me, I had changed the slide and forgotten it. Okay, so we can look at the prevalence, sensitivity, and specificity. First of all, your prevalence is, very briefly, your prevalence is simply how many people in the population of 1,000 people actually have the diagnosis. So it's these two values out of the total people, 36%. So 36% of people in this population have, in this case, a hearing problem. The sensitivity of the test, these prevalence is important because if you're looking at a rare disease, then if it has a low prevalence, all the rest of your statistics can be an issue. Sensitivity is how many people are captured by the test, are true positives, out of the people who really have it. So what proportion of people who really have it, that 360 value, are you testing positive? Are you capturing with your test? And that is then going to be 320 divided by 40 or divided by 360, which is 89%. And how good is that? You can compare this to information you can find out about COVID testing. Is how sensitive is the test? How many true positives out of all the positives is the test detecting? And we would like that to be 90, 95%. The test is accurate. And the problems when the test is inaccurate are particularly if it is a very important disease and you really, really, really want to detect it. The specificity is the ability of the test to screen out those who don't have the disease. So that's your people who really don't have disease, 240, and who also are, or people who are truly don't have the disease and test negative for the disease. So they don't have hearing problems and we don't think they have hearing problems. So we don't even take those for diagnostic testing. And that is your 240 who you say, I'm not even going to take them for diagnostic testing, plus your 400 who you do think have the disease and don't. And you can wonder for what purpose is this a good test? You might find this in something like a screening test because you have a lot of people, you are making correct diagnoses for a large number of people in this quadrant. So you're not sending them to clinical assessment. And they shouldn't be sent to clinical assessment, and that's appropriate. The problem with this test that you might not want to make it a screening test is in the case where the further testing is very expensive. So the problem here is that you have a lot of people who are tested positive, therefore go on to screening. I'm sorry, they go on from screening to the clinical setting. It turns out they don't have the diagnosis and you spend a lot of money on them. You have disrupted their lives by making them think, oh, maybe I am sick, etc. And so when you have a lot of people in this quadrant and the diagnosis is expensive and possibly troublesome, then you have probably a poor test. But again, it depends on the method. If you are trying to optimize sensitivity, you're going to do that at the price of something else. So all of this sort of decision depends on the purpose of the test. Okay, so there are problems with these criterion studies, mostly that we don't have a criterion. And that may be because for reasons of safety, we can't send people on to a diagnostic assessment who don't pass the test. A good example of this, and there are many examples, are when people get a certificate in life-saving. When they are finally tested for the certificate, they try to save an instructor who is pretending to be drowning. Now, let's say they failed that test. What we want to know is, in real life, in the diagnostic situation, would they fail that test? In the criterion, the gold standard, the authentic circumstance, would they fail that test? To find that out in a validation study using predictive validity, what we have to do is, after they failed that test, set them in the situation where someone was truly drowning and find out, wow, they couldn't rescue them after all. So we are never going to do that. And so in that case, we don't know the criterion, or we can't use it. We might know it, but we can't use it. Sometimes we don't know it. So we've talked a lot previously about what is a high school exit exam trying to predict? Is it trying to predict, if anything, is it trying to predict college performance? Well, not really, because we don't expect everyone who goes to high school to go to college, who finishes high school to go to college. Is it trying to predict job performance? Is it trying to predict overall membership in society? We don't know. And so we can't really relate the scores on a high school exit exam to any known quantification later in life. Sometimes you have restriction of range in the criterion. So the SAT is almost entirely used to predict freshman GPA. And the problem with that is that we don't really know whether or not very low scores in the SAT predict very low freshman GPA, because people with very low SAT scores don't get into college. So we assume, based on the other data at higher levels of the SAT, that their freshman GPA would be low, but we usually don't have any data to actually demonstrate that. The schools that very low SATs would be admitted to are probably schools that are quite different in nature than schools that accept students with higher SATs, and that's called the restriction of range. We, in our criterion variable, freshman GPA, we don't have a lot of people who failed the SAT, not failed the SAT, but scored, a 200, 300 on any particular test. And my favorite example of this is when we do have very good prediction, but what we're trying to predict isn't an appropriate thing for the predictor. So the story that I was always told about this is that a bank, let's call it a bank, was looking to predict who would stay in a bank teller position for 5 years or more, because they wanted a stable set of employees. And they found a good predictor, or really a pair of good predictors. But the construct, if there was one, that the predictors measured was an accurate predictor of bank teller retention. And this was like in the 1950s. But it didn't really have anything to do with being a bank teller. And in fact, the predictive variable would no longer be allowed on an application. So, or for decision making. And the predictive variable at that time, 1950s or so, there were really a combination of them, which was that if a applicant was a female in the range of 18 to 30, that was a good predictor that she would not stay in the position 5 years or more. That's because what it was a predictor of was pregnancy. So you had good prediction for pregnancy, but the bank teller position was merely incidental or correlated through multiple other variables. And it, for instance, changed over time, over decades, to be probably a much less valid predictor. So all of those things are things to consider in predictive studies, and one of the reasons why we don't have more in educational testing, some of the reasons why. So another reason that we look carefully at criterion-related evidence is because sometimes looking at simple test prediction can lead to misinterpretations due to bias in the relationship between the score and the criterion. And one of the questions that we ask is whether or not the validity of the score interpretations or uses is the same for different subgroups of the population. So are the predictions the same for a given score regardless of group membership? Now, this is an entirely empirical method. It uses regression equations, and I'm going to show you a couple of examples of possible bias. And as always with bias, if you detect it statistically, you want to go and look at where it's coming from. It usually is, almost always is going to be considered problematic, but it is often not direct bias. It is often bias that is related to other sources of disparities. And you have to make judgments about, do you want to throw out a test because the test results are reflecting systemic disparities, or do you want to take other actions so that you can continue to use the test, but otherwise take into consideration those disparities? They all become complicated and policy types of arguments. But we're going to just look at some of the statistical relationships that indicate that bias may be an issue. So if we do a regression on of outcome tests, so we have, say, a criterion on aptitude test scores, then we may see a pattern like this when we disaggregate the data by sex. So we have the aptitude test scores on our x-axis and the outcome test scores on our y-axis. And let's say that the outcome is a criterion, that it is, we can say that the aptitude is SAT and the outcome is freshman GPA. So what we see is that these two lines of best fit to the data that relate aptitude to outcome, are parallel. They have in common this: if you don't disaggregate them, the slash line is their common equation. What's different when you disaggregate by sex is what we call, what is mathematically the y-intercept, which is where the line of best fit crosses the y-axis for both groups. And the groups cross the y-axis at different places. So this is evidence of a disparity. What it shows us, this difference in the intercept, suggests, or actually it just shows us, but it's suggesting that we don't know if it's going to be true for a population. We don't really know why it's true. We don't know if it would be true in other contexts, or is it a case of the aptitude test scores, the outcome test scores? Where is the bias? There are a lot of things we still don't know. But we know that there are differences in y-intercepts for these two groups. And particularly, to be very specific, males with low aptitudes score lower on the outcome than females with low aptitudes. So these two groups have the same aptitude at each of the levels. Males and females here have the same value on the x-axis. They have the same value on the y-axis. But males always score lower on the outcome, even though they had the same aptitude to start with. It appears to be some kind of discrimination in outcomes for males. There's a lot we don't know here, but that's what it looks like. So let's look at a different example. These are slope differences. In other words, in this example here on the left, the intercept, the place where both of these would cross the imaginary y-axis, are very similar. They're very close together. So at the low aptitude range, males and females score very much alike. But one of these, the females, has a very steep slope, and the other, the males, has a very gentle slope. And the medium slope, dashed line slope, is only the one that you obtain if you don't disaggregate by sex, which is one of the reasons that you want to look at things like sex differences, because otherwise you wouldn't see it at all. At the high end of aptitude, men, for the difference between low aptitude and high aptitude men, there's very little difference in outcome. For the difference between low aptitude women and high aptitude women, there's a great difference in outcomes. So in this case, females get a lot more bang for their buck in outcome by having the same difference in aptitudes as males. And the one on the further right is another kind. Both of these are considered interactions. Interactions between sex and aptitude in their relationship to outcome. In this, you have a regression lines that switch direction. And at the lower end of the aptitude scale, the difference between males, which is, I'm taking as the flatter line, and females, is in favor of males. So males with low aptitude do better on the outcome than females with low aptitude. But when you look at males with high aptitude, females do better than males. So it's a strange outcome, and one that you definitely want to investigate. The scale, aptitude scale behaves, functions differently for different groups. And that's pretty much always a problem. It's a problem at the item level, where we look at it in terms of differential item functioning, and it's a problem at the whole test level. Other external structural evidence can be done without a criterion variable. And we call those, they're kind of classically put less under our, the term criterion validity isn't used so much in contemporary test theory or validation theory. And it's just called external structural evidence in general. And criterion is part of it. And so are convergent and discriminant sources of evidence. And this is where we look at the relationships between scale scores and other variables that we theorize will be related to our scale that we're validating. And this isn't really the same, it isn't the same thing as testing theory. It's testing technical quality of scales. And so when you say a theoretically related variable, you know, something that you might be looking at would be, you have a self-efficacy measure of teacher beliefs about teaching students with disabilities, teacher self-efficacy for teaching students with disabilities. There is such a thing. I can't remember its acronym. And you have created an alternate measure of that. You have created I'm trying to think how else besides a Likert scale you could use for teacher self-efficacy. But you've created, the one that you have found is a Likert scale, and you've created a vignette-based scale that's just answered in a yes or no format. But you expect these things to be measuring exactly the same thing. And so you want to see whether, if you apply both scales, the results converge. Because if they don't converge, that's a problem. You would expect them to be measuring the same thing. They're both self-efficacy for teaching students with disabilities. And so their results should be quite similar. Now, they won't be completely similar because there are what we call method effects. So if one of them's vignette-based, that might be a little bit more obscure. If it's Likert-based, it might be get some superficial answering, who knows, but they won't be perfectly related, but they should be highly correlated. And then you're going to have less theoretically related variables. Now, for a good discriminant test, you don't want those to be opposite variables. You don't want the variable that you are relating your self-efficacy for teaching disabilities to be something kind of opposite, like anxiety around students with disabilities. That's not discriminating between two similar things. It's expecting things to be opposite. So that's not what you're looking at. What you're looking at is, well, I want to know, A, are two measures of self-efficacy with teaching students with disabilities, do they yield similar scores? In which case, maybe mine is better for reasons that I can argue, but it's consistent. It looks like it's measuring the same content. And then if I look at my scale for teaching students with disabilities, self-efficacy, then how does that compare with general self-efficacy? So I should reasonably expect that it will be related, but maybe not as highly as a measure of self-efficacy that's particular to students with disability. So then we go to, if you're doing this really thoroughly, you get to something called the multi-trait, multi-method approach. So this is kind of rarely done thoroughly, but it is bit of a gold standard for looking at convergent and discriminant evidence. And this is how the results of a multi-method, multi-trait approach will be all the different things you can capture with it and the sorts of questions it can answer. Don't worry about this too much. I'm going to go through the things and then y'all get a rest. So what this particular study does is it measures 3 traits, trait A, B, and C, using 3 methods, method 1, method 2, and method 3. So you can say it measures anxiety, depression, and mood disorder using self-report, clinical observation, and spousal report. I like that. Okay, I'm going to write down what I said so I can come back to it. Anxiety, depression, and mood disorder using self-report, clinical report, and spousal report. Okay, so we're going to start just by looking at our kind of blue diagonal. And that's the reliability diagonal. That's easy. That is the correlation of the thing with itself. So if you look at this 0.89 up at the top left, you're going to see that if you look at method 1, trait 1, correlated with method 1, trait 1, in other words, anxiety with self-report, correlated with itself, that's its reliability, the thing with itself. This value here, another point, well, not to use another 0.09, I'll go down to this 0.76, the third on the diagonal, which is going to be trait C, which is mood disorder, correlated, trait C in the spousal report, trait C in the spousal report. So that's its reliability. And you see the reliabilities of each of these scales measuring mood disorder by spousal report has a reliability. So let's say it's test retest. You talk to the spouse once, get the spousal report on mood disorder symptoms once, and get the spousal report on mood disorder symptoms twice. And that's the correlation between the 2 occasions, test retest. Okay, so that's our reliability diagonal. And we brought that in through probably a whole different study. It just goes in the diagonal. Now we come to the orange triangles. And the orange triangles are called, and by the way, you're never going to remember all of this. Whenever I look at one of these, I have to think about it for several minutes. So the orange blocks, in this case orange, they're not always written the same way. That's not traditional, are what we call the heterotrait, heteromethod triangles. So they're when you have different traits, say anxiety versus depression, and different methods of measuring them, say self-report versus with clinical report. So neither the method of measurement nor the object of measurement are the same. Both things are different, so you would expect these to be low. So let's look bottom right-hand corner, top or bottom left-hand corner, I'm sorry, value 0.23. This is method 3, which would be spousal report on trait B. Let me find my annotation. Method 3, which is spousal report on trait B, which is depression. Correlated with, so you've asked spouses to report depression, and you're correlating those scores with trait A, method 1. So you've asked spouses to report depression, you have those scores, and you're correlating those scores with asking people themselves to report anxiety. So how highly would you expect what your spouse tells a surveyor about your depression with what, your depression with what you say about your anxiety? Because those are two different sources of information and information about two different things, they shouldn't be correlated very strongly. Now they are going to be correlated to some extent because everything in the world is correlated, but they should be correlated less than anything else. Your heterotrait, heteromethod triangles should, in the multi-trait, multi-method scenario, have the lowest correlations among anything because they're correlating things that are unlike in both dimensions, traits and methods. But note that these things are not whoppingly unlike. They're not, you're not correlating it with enthusiasm and gregariousness. That would be kind of a straw man argument. So then we're going to go on to one of the others, which is the validity diagonal. This is the one that you're really hoping is going to be high. And what are you looking at? You're looking at, let's see, the one that this arrow particularly points to, so that I can just go into a little of particular using it as an example. That's the 0.58, where you're looking at trait C, which is mood disorder, as measured by method 3, spousal report, with trait C, mood disorder, as measured by clinician report. So you're looking at convergence. You're looking at whether or not, when two people are asked to report on the same thing, they come up with a common result. So for instance, another place we can look is the mood disorder here. This is a validity diagonal. And this one represents mood disorder as reported by the clinician with mood disorder as reported by the self, method 1. So do the clinician and I agree about my symptoms of mood disorder? Does the clinician and my spouse agree about my symptoms of mood disorder? And that is what shows up on your validity diagonal. Do I, method 1, and my spouse, method 3, agree about my symptoms of anxiety, trait A? So you want these to be high. Now they're not going to be whoppingly high because you're always going to have different perspectives, but you want them to be high relative to other things in the index. And now we're going to go one more, which is the heterotrait monomethod triangles, which are bright pink. And unfortunately, in this case, these are high. We want our heterotrait, heteromethod blocks, triangles to be low. We want our validity diagonals to be high. So these are moderately high validity diagonals. We're doing okay. We want our reliabilities to be high. Doing pretty well with that. But unfortunately, our heterotrait monomethod diagonals are pretty high, particularly in these two blocks. So what does that mean? Let me get my handy annotation so that I can examine one at a time. Let's look at a particularly high one. Let's look at this 0.67 here, which is as high or higher than any validity diagonal. Excuse me, any validity diagonal. So what does this mean? This means that here I am, I'm measuring both two different traits by asking the spouse. I'm in method 3, asking the spouse. And I'm asking the spouse about anxiety, and I'm asking the spouse about depression for a given person. The spouse agrees equally with symptoms of anxiety and depression. The spouse also sees mood disorder in the same way that they see anxiety or depression. It all looks alike to the spouse. What those seem to have in common is not the differences in the diagnoses. It's the commonality of being the spouse. So the source of the report results in high correlations among the diagnosis of the traits. This is what we call a method bias. You're relying on one method, which results in different measured constructs appearing to converge. And so it is a method bias, and it's something you don't want to see, and it's a particularly nice feature of the multi-trait, multi-method approach, that it can clearly illustrate that, for instance, in this particular example, you have evidence of a method bias, and that there are high correlations related to method regardless of the trait that's measured. And that is all for this presentation. I think it's probably plenty. I hope that you enjoyed it. The multi-trait, multi-method approach particularly is a highly sought after, fairly rarely performed approach to validation, but you can kind of pick off little pieces of it, and you don't have to do the whole thing quite as thoroughly as it's done in this example. And the diagnostic classification is not only interesting, but is pertinent to the sorts of things we're reading about with COVID tests. So it definitely might give you something to look into about the accuracy, the sensitivity, and the specificity of the tests for the disease virus that we're unfortunately suffering under in 2020 and 2021. Thank you very much for your participation throughout and your enthusiasm, which I know you share.